This is slide number 26 and I am your presenter Asloob Mudassar. Now we are presenting an example so that we can calculate the object special frequencies and the object Fourier frequencies and see evaluate the comparison between them, or see that if there is any relationship between them or not. So this is example 2. Let's consider a phase object with a spatial frequency equal to 0 at the center. The object that we have shown on the right, in the center there is no spatial frequency, and we can say that the spatial frequency it is 0 over there in the object, and that the spatial frequency increases along both the x and y axes and also in all other directions, and we can write the object 6 as O6, which is the function of x and y, is equal to 1, which is the amplitude multiplied by the phase factor e to the power iota pi. Within the bracket we have mu x into x square plus mu y into y square. Now you know that this is actually a phase object. In the phase object only the thickness of the object varies on a transparent glass plate, but you know that we cannot visualize the thickness with a human eye. Human eye cannot realize the thickness variation. So what we have done is that we have depicted that object in terms of the amplitude variation. So actually this object on the right is actually a phase object, and we have indicated their amplitude, their phase variation in terms of the amplitude, so that we can see this object. So this is object number 6, and you know that it's the mu x and mu y, they are the same in both directions. So we can set mu x and mu y equal to 0. This is what we have stated, that the parameters mu x comma mu y are real constants, and due to object symmetry they may be set equal to each other or equal to some other constant mu. So mu x is equal to mu y is equal to mu. And you know that there is another figure, the second one. This is actually a cross section of the above figure in the center. So from the center, either horizontal center or the vertical cross section, you will see this variation. So you see that we have a main lobe in the center of this figure, and you know that the spatial frequency increases on both the left hand side and the right hand side of this cross sectional view. Now the size of the object is infinite with the phi of x is equal to pi into mu into x square plus y square. The size of our object is infinite. This is not limited, but you know that we have shown only the object, but keep it in mind that the size of this object is infinite, and the object is not an amplitude object, but it is a phase object. And the phase is given by that we have given phi of xy. So this is the phase distribution over that object, and that is equal to pi into mu into within the bracket we have x square plus y square. Now the spatial frequencies that we can compute for this phi function, and you know that we have studied the formulas previously, and we have to calculate the rate of change of phi with respect to x in order to find f0x divided by 2 pi, and then we have to calculate the spatial frequencies in the y direction. For that one we take the Fourier transform, we take the partial derivative of phi with respect to y, and then we shall divide the whole by 2 pi. So this is what we have evaluated according to one of the previous according to one of our formula given in some of the previous slides, that the spatial frequency of the object along the x direction is equal to mu x, and the spatial frequency of the object along the y direction is f of 0y is equal to mu y. Actually both these are equal, and these are also very clear from the object that the spatial frequency in both directions are the same. Now so we have calculated the spatial frequencies of the object. The next one is to calculate the Fourier frequencies. To compute the Fourier frequencies, we have to compute the Fourier transform. Let's restrict the dimensions of the object in the rectangle of size 2x and 2y along the x and y directions with the object centered at the origin. So you see that now we are setting the dimensions of this object. From the center on the left we have the dimension equal to capital X, and along the negative X axis we have the dimension equal to minus capital X, and similarly along the positive Y direction we have plus Y, and along the minus direction we have minus Y. So over we have actually fitted, you see that in this object I have fitted the aperture which is black in the shape, so no light can pass through the black region, so the light will only pass through this object, and the dimensions of this object, the total dimension of this object along the horizontal axis is 2x, and along the horizontal axis is 2y. Okay, now we have to calculate the Fourier transform. Outside the rectangle, the object is assumed to be 0, as this will not affect the spatial frequencies of the object. So we have calculated these spatial frequencies, these two one, that is f0x and f0y, and if we limit that object in a rectangle of size 2x and 2y, this data will not be changed. But of course the Fourier transform will matter, so we cannot evaluate the integrals from minus infinity to infinity for the Fourier transform. That's why we have put the limit, or we have put a square aperture, or the square aperture on the object centered on the object of dimensions 2x and 2y, so that we can evaluate the Fourier integral very easily. So in the Fourier integral we have capital O6 on the left hand side with as a function of a Fourier frequencies fx and fy, and on the right hand side we have given the formula for the Fourier transform. You are familiar with this formula, and we have plugged in the function O6, which is a function of x and y. So now in the next step, in the second step, we have substituted the values of O6, which is e to the power iota pi into, within the bracket we have mu x into x square plus mu y into y square, and in the next we have set the values of mu x is equal to mu y is equal to mu, as we have stated earlier. So now, and we have also separated the integrals into integrals as a function of x and integral as a function of y, because these two integrals are separable into x and y coordinates. So on the left hand we have the integral as a function of x, and we have denoted it by capital O with a subscript of 6x as a function of fx, and on the right hand side the integral has been labeled as capital O as with the subscript of 6y and as a function of fy. So these two are the integrals that these two are integrals, you know that these are identical integrals. So what we have to do is that we have to evaluate any one of the integrals. Say for example O6x integrals will be evaluated next, and then we can write down the value of the O6y integrals just by replacing the x variable with the y variables. Okay, now we have the integrals which is O6x, which is a function of fx only, and we have shown the integrals on the right, but you know that the limit has been changed from minus capital X to capital X, because in the rest of the region the integral will be 0, so only the integral will exist in these limits minus x to capital X, and this is the integral that we have shown. Now we have now you see that there are two in the exponential we have x square, and in the second exponential we have x. We have to complete the square so that we can solve the integral, and we have written down after completing the square the integral on the rightmost side of this one, which is some constant factor has been taken out from the integral, which is e to the power minus iota pi fx square over mu, and the integral is from minus capital X to plus capital X, and the integrand is e to the power iota pi by 2, and within the square bracket we have 2 mu square root of 2 mu multiplied by x minus fx over mu the whole square, and this is the integrand. This is what we have to solve. But you know that in order to solve and in order to simplify the integral, for the solution we are making a substitution that t with a subscript of x is equal to square root of 2 mu multiplied by x minus fx over mu. So we are making this substitution, and for this substitution we are calculating the lower limit. So replace small x by capital minus x in order to calculate the lower limit, which we have labeled as alpha of 1x, and then in the tx expression replace x by capital X, so that you can get the upper limit, which is alpha 2x. So we have given alpha 1x as the lower limit and alpha 2x as the upper limit. and there is some constant factors over there. As a result of this substitution, we are introducing that constant to be replaced by beta x. That will be equal to e to the power minus iota pi fx square over mu divided by square root of 2 mu. To write O6x as a function of x in more concise form, which is given as this one. So you see that this 6x of x is now represented as beta of x, and in the curly bracket we have splitted the integral into two parts, that is the limit from alpha 1x to 0 and from 0 to alpha 2x. Actually there is a plus sign over here that we have missed over here. So in these two integrals there is a plus sign. So okay. And then we have evaluated the other integral. We have written that one also there. Actually this is again, you know that this is the plus sign over here, but I have used it an equal sign. So this is the plus beta x, and within the curly bracket we have a minus the same integral, but you know that now the second integral we have written from 0 to alpha 1x into e to the power iota pi by 2 tx square into dtx, and the other integral sorry, there is no plus sign, because the integral goes from alpha 1 to alpha 1x to 0, and then from 0 to alpha 2x. So this is one integral, you know that, and because we are only solving this only single integral, so this integral now is equal to beta x, and we have represented this integral in such a way that we have multiplied the first integral with a negative sign, so that we can write integral from 0 to alpha 1x as the limits, and because the other integral is also with the limits from 0 to alpha 2x, and you know that the integrand in both the integrals are the same. Okay, now we can expand these exponential functions as a function of cos of something plus iota times of something. So you see that each of these exponential factor can be expanded as cos of pi by 2 into tx square plus iota sine of pi by 2 into tx square. This is what we have demonstrated for each of the integrals. So for one integral we have written beta x is equal to this one. You can see that we have represented the exponential as cos of pi by 2 into tx square dtx, and then we have represented minus iota times sine of pi by 2 tx square dtx, and the other one we have shown for the other integral also there. But this is not, remember that this is a mistake, that there is no positive sign over here, because over here in that one the two integrals, these two integrals are multiplying with each other. So here there is a multiplication sign rather than the positive sign over here. So with the second row you should assume a multiplication sign with the beta x, and then we have expanded the sign second integral over here. So the first integral and the second integral have been expanded in terms of the cos and the sine. Now we are going to define, because these integrals are not cannot be solved. These can be solved only numerically. So we are going to introduce these integrals as the Fresnel integral. So Fresnel C of alpha is equal to the integral from 0 to alpha cos of pi by 2 t square into dt. So you know that if you remember the integrand, if the integrand is cos of pi by 2 t square and the limit from 0 to alpha, then just in the Fresnel in the Fresnel expression we represent only the upper limit, which is alpha. So the next one is a sine integral, and we represent it as a Fresnel S, and the upper limit is alpha. So we have shown the upper limit only. So you can identify that how you can define the Fresnel C with the cos function, and you can define the Fresnel S with the sine function. Both have the same arguments, and only you will show them the lower limits in both are 0. The upper limit is alpha, for example. So you can represent with the upper limit of these functions only. That is Fresnel C with a square bracket of alpha and Fresnel S of alpha. So these there are tables that can give you the value of if you substitute the upper limits in these from the table, you can find out the value of the Fresnel C integral and the Fresnel S integral, and you can substitute these values in the next one in order to solve them. So you know that in the previous integral we have combined the cosine terms, that is the Fresnel C integrals and the iota times Fresnel S integrals, so that we can write iota common and we can combine the cos terms, that is the Fresnel C integrals and Fresnel S integrals. And similarly, you know that for O6 we can similarly write for the O6y integrals as a function of y. The same expression is there, but only that the limit will be changed, because in the previous one the limit was alpha 2x. Now we have the alpha 2y, because we are changing the x variable with the y variable. The rest of the quantities are the same. So beta x will be replaced by beta y. Fresnel C, in the Fresnel C the upper limit was alpha 2x. Now this will be replaced by alpha 2y in all these integrals, and if we have alpha 1x in the previous integral, that will be represented by alpha 1y. So just replace x by y in order to get the expression for O6y. So let's choose the parameters. Mu is equal to 1, x is equal to capital X is equal to 10. And you know that we have calculated previously the spatial frequency along the x direction was equal to mu x. So put the value of mu, which is 1, put the value of x, which is equal to 10, and the value is 10. So the spatial frequency of the object along the x direction for the given object is 10. Now we want to plot the function. Which function? That is O6. Let's plot O6, but you know that O6 contains iota, so we are going to plot the absolute value of O6. So here we are going to plot the absolute value of O6 versus F6. F6 is the spatial frequency, you know that the variable in the spatial coordinates or the variable in the Fourier plane. So we are going to plot the mod value of the O6 versus Fx. This is shown in the figure. And you see that the figure shows that the Fourier spectrum has significant values in the region. Notice on the horizontal axis that the values of this function, which we have plotted in the figure, you can see that the values lies from the significant values lies from minus 10 to the plus 10, and beyond that the function immediately goes to 0 and decays and goes to 0. So the mean values of this plot, that is the plot of absolute value of the plot of O6x lies in the region from minus 10 to plus 10, and we have depicted that one as fx is greater than equal to minus f0x and is less than equal to plus f0x. So the Fourier frequency lies in the range defined by the object spatial frequencies, from minus object spatial frequencies to the plus object frequencies. The Fourier, you know that now region is identified, that it goes from minus 10 to the plus 10 along the fx direction, as obvious from the figure, as obvious from the plot. The Fourier frequencies and the spatial frequencies are obviously related in this case. Let's try the other parameters. So we are now going to try three parameters. Mu is equal to 0.5 and x and capital X is equal to 10 in both cases. Mu is equal to 2 and x is the same, which is equal to 10 in the second case, and mu is equal to 3 and x is equal to capital X is equal to 10 in the third case. So you see that we can calculate similarly the object spatial frequencies along the x direction as we have mentioned previously, and we can plot the absolute value of O6 along the horizontal frequency fx. So you know that we have plotted in each of these cases the absolute value of O6 fx as we have plotted in this figure, and along the horizontal parameter is fx. So the three plots corresponding to these three parameters are shown over here. Now you see, you can compare that Okay, now you can, if you calculate the f0x, which is the mu x, so mu multiplied by this x will be equal to 0.5 or multiplied by 10 is equal to 5. So you see that, you know that this figure, the first one on the left hand side, has significant values in the range from -5 to plus 5. In the second case, you have a mu multiplied mu with 10 to get 20, and 20 is the spatial frequency of the object along the x direction, and you can see that from the Fourier plot that the significant values of this plot lies from -20 to +20. And in the third case, you have a mu is equal to 3, capital X is equal to 10, so multiply these two to get 30. So f0x is equal to 30 in this case, and look at the Fourier frequencies. The Fourier frequencies, the significant values of those Fourier frequencies lies in the range from -30 to +30. So you know, so you see that here again this condition is applicable, that fx, Fourier frequency, lies in the region from -f0x to plus f0x, that is the object spatial frequencies along the x direction also specifies the region of the Fourier spectrum. So a definite relationship exists in this example. Now the Fourier frequencies and the spatial frequencies are obviously related for all values of mu. Now there are some two important points. There is a proven fact that the compression of data in the space domain will result in expansion of data in the Fourier domain and vice versa. As you can see from the previous three graphs, this is very well explained. The note 2 is equivalently, the higher the spatial frequency contained in an object, the larger will be the dimension of its Fourier spectrum and vice versa. This can also be established from the previous condition. So with this one, this is the end of slide number 26.